So welcome. These are our notes for absolute value graphs. And we're going to begin by looking at the parent graph of an absolute value function. So if you're in your TI-84 graphing calculator or in Desmos, you're going to enter the function absolute value of x in the y equals. And then you can do zoom 6, zoom standard to look at your parent graph. And the parent graph of the absolute value function makes a V shape. So it's going to go through 0, 0 for the vertex, that's the origin. Then it's going to pass through the point 1, 1 and negative 1, negative 1. And it's going to make a V shape. So again, that passes through 1, 1 and negative 1, 1. And the vertex is the point at the origin where this V shape comes together. Okay, if we take a look at transformations, okay, how does adding a number to the function change its graph? So if we go over here to Desmos, we're going to add a number to the end of this function, so plus 3, and we see that adding 3 to the end of the function as a constant moves the absolute value V shape up 3 units. If instead of a plus 3, I do a minus 3, now I see that it's moved the vertex down 3 units from 0, 0 to 0, negative 3. And that is a vertical translation. Moving your graph up or down is going to translate it vertically, the number that is added or subtracted from the absolute value graph. On the first page of the notes, you'll see the transformation form of an absolute value equation, and the k, the constant added to the end of the function, is called a vertical translation. That moves or shifts the graph up or down. A minus k is going to move the graph down k units. A plus k is going to move the graph up k units. Okay, next, let's take a look at this value h inside the absolute value function with the x. So let's see how adding a number inside the function changes that graph versus subtracting a number from inside the function with the x. So if I go back to Desmos or that graphing calculator, okay, this time we're going to subtract 3 from inside the absolute value function. And we see that the parent graph, the vertex at 0, 0, shifted 1, 2, 3 units to the right. So x minus k is going to shift that graph to the right k units. If instead of subtracting, we add, so absolute value of the quantity x plus 3, that's going to shift our vertex 1, 2, 3 units to the left. And so we see that the h value affects the horizontal translation. It's going to move the graph to the left or the right. When we have absolute value of the quantity x minus h, right, that makes it a positive h. That's why we're moving to the right. In the absolute value of the quantity x plus h, that form is x minus h. So to get a plus, we'd have x minus negative h. And the negative on the h is what shifts the graph to the left. Since the vertical translation, the k, moves up and down, that k turns out to be the y-coordinate of our vertex. The horizontal translation, that affects the x-coordinate of our vertex. So the vertex will always be located at h, comma, k. So let's take a look again at Desmos and put in a new function. Y is equal to the absolute value of x minus 4. And then inside of our absolute value, let's do a plus 2. Okay, so I want to take that 4 and move it to the outside. There we go. Minus 4. Okay, there we are. So we can see from this, function that the vertex of the graph is located at -2, -4. Okay, this x plus 2 shifted the graph 2 units to the left. The minus 4 shifted the vertex down to negative 4. And there's our vertex at negative 2, negative 4. If I wanted an absolute value function that had its vertex at 3, 7, then I would change this to move to the right 3. And then I change the k to go up 7. And there's my vertex at 3, 7. Okay, so next transformation that we want to consider is multiplying the function by a negative out front of the absolute value symbol. And when we put that negative in the front, so we'll get rid of this plus 3 and put a negative out there, we see that the graph flips upside down. Right? Again, there's our parent function. We put a negative in front of the function and we get the reflection over the x-axis. It flips the whole thing upside down. That's going to happen even when we have other transformations. So here's my function that I created that had a vertex at 3, 7. If I put a negative in the front, watch it flip upside down. There it goes. Right? We get rid of the negative, it opens up. We put the negative back in, and it flips upside down. And that is affected by the A in our transformation form. So the A, when it is negative, your absolute value V shape opens down because there's a reflection, a flip, or a mirror image over the x-axis. If the A is positive, then that V-shaped graph opens up. Okay, and then we're going to look at dilations. So how does multiplying the function by a number greater than 1 change its graph? So if we look back at Desmos and play with that a little bit, okay, we can multiply this function by 3. So here's my parent graph. Here's multiplying that parent graph by 3. Do you see how it narrows the V shape? Instead of the slope from the vertex being up 1 to the right 1, we go up 1, 2, 3 into the right 1. And that's called a vertical stretch. We're stretching the slope up higher. That makes a narrower V shape. If instead of a 3, I were to do a 1 over 3, so 1/3. Okay, now we can see compared to the parent graph, there's my parent graph with a slope up 1 over 1. The 1/3 changes that slope up 1 over 3. So it's widening that V shape. The wider V shape is going to be called a vertical shrink because we're shrinking the distance toward the x-axis. So that is a dilation, a narrowing or widening, and it's affected by the absolute value of the A, the number multiplied out front of the function. When the absolute value of A is greater than 1, that narrows the graph. The V shape will be skinny, tall and skinny. If the absolute value of A is equal to 1, there is no dilation. If the absolute value of A is less than 1, so that's a fraction between 0 and 1, then it's going to widen that V shape with a vertical shrink. So let's take a look at example 1 in the notes. Using the transformation form we looked at, here's the 3, that's the number multiplied out front, that's the A. The H is after the X inside of the absolute value, it's being added or subtracted from the X. And then the K is outside of the function, that's the constant at the end. Remember that we learned the vertex is located at H, K. So our vertex is going to be at 2, 4. Oh, 2, negative 4, sorry. So we're going to come down to our graph. We're going to go 2 units to the right and down 1, 2, 3, 4. And there's the vertex at 2, negative 4. Okay, because the A is positive, I know that this V-shaped graph opens up. And the dilation is the absolute value of the A. The absolute value of 3 is 3. And that's going to be the slope that I use going from the vertex. So we're going to go up 1, 2, 3 and to the right 1. up 1, 2, 3 to the right 1, up 1, 2, 3 and to the right 1. I can also use that slope going to the left because this graph makes a V shape. So I'm going to start at my vertex again, go up 1, 2, 3 and to the left 1, up 1, 2, 3 to the left 1, up 1, 2, 3 and to the left 1. And now I can connect those points to make my absolute value graph. Right, in example B, we have our A is negative 1/2. The H is the opposite sign here, so the H is going to be -3. The K keeps the same sign, and that's a +2. My vertex is at H, comma K, so the vertex is at -3, comma 2. Right? Remember, the x plus 3 takes us to the left, so the H is negative. So I start at the vertex, or at the origin to find the vertex. I go to the left, 1, 2, 3, and up 1, 2. And there's the point for my vertex. Because the A is less than 0, it's a negative A, this absolute value V shape is going to open down. And the dilation is the absolute value of the A. That's a 1/2. So we're going to have a vertical shrink. We're going to start at the vertex. We're going to go down 1 and to the left and right 2 units. Down 1 to the left and right 2 units. And then we can use those guide points to sketch the V shape. So in example 1, we see the vertical stretch, the narrowing of the graph with the dilation of 3. In B, we see a vertical shrink, a widening of the graph with the dilation of 1/2.